Our topic is sample mislabeling correction. So, what is sample mislabeling? Is that the labels are misplaced by machine or human error. If this happens in a hospital lab, what it may cause? Let's see.
Mr. McKenna, you're cancer free. The biopsy looked like adenocarcinoma, but it wasn't. Harmless lesions on your lungs. You're fine. I don't get it. I just accepted an offer on my house. I've had 3 goodbye parties. I'm buying plane tickets to Venice.
You can still use those if you're alive.
I have to pay a $6,000 broker commission on a house I'm not selling. Money I don't have. Thank you for letting me know.
A patient was diagnosed with cancer, but it was not until 3 months later that the doctor told him that he was cancer free just because of disease mislabeling. The result is that the doctor was sued by the patient. Actually, this also happens in our lives. Mislabeling will make lots of troubles. So, this explains what the problem is of our project right now. We intend to make better labels classification. During the whole project, we used Apex Spark, a distributed processing system, to process all the data and explore our machine learning algorithms in Amazon Elastic MapReduce. First, we need to know that there are relations between RNAs and proteins. In the first step, the information in DNA is transferred to a messenger RNA mRNA molecule by way of a process called transcription. During translation, which is the second major step in gene expression, the mRNA is read according to the genetic code. From this short video, we can see that proteins are synthesized through RNAs. The words GGU and the CCA, as we can see, can be seen as a key pair. So, if we find the relations from these two data, we are able to judge those mislabeling. So, first of all, we intend to do some pre-process for our data. For protein data set, each test sample contains more than 4,000 data points, and for RNA dataset, there are even more than 17,000 data points per sample. If we use all of these data points, the calculation is extremely large even for Amazon Web Service. So we need dimensionality reduction technology, like this sentence, to find out what Mike is doing. We don't need to read and understand every word in the sentence. All we need is the important words. Mike is reading a book. The red words dimensionality reduction can do the same thing to our data set. We labeled the data by male, female, MSI low, and MSI high as given in the clinic file. We pick the data points that can split the data by label clearest to keep. After reduction, the size for both protein and RNA data size are minimized. We have RNA and protein data size from same 80 test sample, and there are mislabeling happens in both data size. Now, we want to generate our own training data. What we do is take one sample data from RNA data sites and combine it with all sample data in protein to form 80 new training data. And we label each new sample one if and only if RNA and protein are from the same test sample. All other new training data are labeled as 0. We do the same process to all sample in RNA dataset, which give us 6,400 new training data. 80 of them are labeled as 1 and the rest of them are labeled 0. So right now we have the positive and the negative training sample pairs. We subtract 50 positive and 50 negative sample pairs to train this neural network. The output of the neural network means the matching probability of the given RNA series and the protein series. After training this network, we will get a model to help us quantify the matching degree. To avoid overfitting too much, we also applied dropout method and got a result of accuracy over 95%. Although the outcome seems pretty good, we still have an issue about whether our trained model can be used on the test site. Because as we know, the neural network works only the training set and the testing set have the same distribution, which is unknown here due to the fact that we only have 80 samples and generated 6,400 sample pairs in this project. Another way to do this matching problem is using traditional machine learning method. Support vector machine with kernels. Support vector machine usually works better when training data set is not that big, and it also deals with the problem that the number of positive and negative sample pairs are not balanced. This is our process of the project. First, we do the task analysis, and then we did dimensionality reduction, and next we explore the relation between the data, and finally we got the results. Next, we will show how to using EMR console to launch a cluster with bootstrap actions and log in Jupyter to run codes to set up our models. And right now, next, I will show how to run our code on the EMR cluster and with the Jupyter. Here we have we have started a EMR cluster on the AWS, and we can see the cluster is waiting for our operation. And right now we can use it to log into the Jupyter. The public DNS of the master is this. I copy it and put it here. Excuse me. And the port. And right now we log into the Jupyter. This is our code, and this file is for the unsupervised learning. We just and right now we restart our kernel and to run this code step by step. It's a little bit time consuming. And this is some functions we will use later. This is all the file we have. And here we prepare the training data, and next we generate the RDD for the cloud computing. And here we apply the PCA method to reduce the dimension. And after this step, there is a picture show the number of component and the energy of the data rest, so we can see how many components we pick will generate the most the perfect data. And next, we use another method quite similar to PCA, that is LDA. It uh, it reduct the dimension by label. So let's run it. And after it, we can see the output. The LDA method says the protein mislabel number is this, and the RNA data mislabel uh, is this, and this is the clinic mislabel number. Yeah, that's our unsupervised learning method. Another one is use SVN, the supervised learning. But SVN, the result is not very satisfying because we don't have enough training set, and the samples are uh, not that large. Yeah, let's let's also run it. Out of charge. We're waiting for the importing the package. Just wait a second. Okay, the kernel is starting. We should wait. Why is this kernel starting so long? Okay, it's ready. And this is function, this is the file. And this is we generate the simple pairs. This is SVN. Training the SVN model. After training, we will get a model to help us predict. Okay. And we can see our training set has 6,400 simple pairs, and the training result says these samples are correctly separated. And next we put our test data in the model and to predict, but the result only says there is only one sample pairs are perfect match, which is unreasonable. So so I think the SVN is not very good here, But if we can get more data, maybe the result will be better. Yeah, that's all.